8.1 when we discussed properties of scatter plots as well as their lines of best fit as an introduction. We're going to go a little bit deeper into it today by creating and fitting a line of best fit utilizing least square regression to do so. Why do we want to find the measure for the best line? We want to make sure that our line has small residuals. And we talked briefly about residuals in lesson 8.1 with respect to the distance between the actual point itself and the line. In order to do that, where we can have small residuals, we have a few options in order to get there. The first one would be to minimize the sum of the magnitudes or the absolute values of those residuals. Another way to do that is to minimize the sum of the square of the residuals, which is called least squares. And why do we care about least squares? They're most commonly used and they're easier to compute by hand and by using software. Also, in many applications, a residual twice as large as another is usually more than twice as bad as another. So here's the least squares. You may notice this formula and noticing the red values there look vaguely and eerily similar to y equals mx plus b because it is. Except our slope and our intercept are backwards, which it is the exact same equation. We have some parameters. We have the intercept, which is beta sub 0 or the point estimate b sub 0. We also have the slope, which is listed as beta sub 1 or b sub 1, and we can interchange those values themselves. We have our predicted y value, what we think should happen, and we have our explanatory variable. There are some conditions, like anything else we've discussed, that need to happen in order for us to be able to utilize the least squares line. They have to be linear. They have to have nearly normal residuals and constant variability. So what does it mean to have linearity? The relationship between our explanatory variable, or the independent variable, and the response variable being the dependent variable, should be linear, a nice straight line. Methods for fitting a nonlinear relationship, if you were to think of a parabolic one or a hyperbolic one, those are available to you in an online extra. However, those techniques are a little further developed, and you most likely probably covered them in Algebra 2 or college algebra. So we can use the scatter plot and a residual plot to help us identify linearity. If we look at the top row, those are scatter plots with the line of best fit already predetermined for us. And if we look a little closer at the bottom picture is the residual plot. Notice with the residual plot, the dots are on the very far left there. The dots are very much above and beyond equivalently. Similarly, it almost appears that way on the far right-hand side. However, when I look at that middle graph, notice it kind of comes up and then it comes down. Perhaps that might be a parabolic type fitting, a parabola, instead of a nice straight line. So most likely when I'm utilizing a scatter plot, linearity probably wouldn't fit very well for that middle graph. Going back to the example we had from lesson 8.1, we said that the expected poverty equation was equal to 64.68 minus 62% times the percent of high school, times the percentage of high school graduates. So when I'm looking at the residual plot associated with our graph here, let's take a look at first the green triangle in the value itself and where it's associated with the the residual plot down below. So if I were to substitute 81%, we could find the residual value by taking the percent that's in poverty, which was given on the last lesson of 10.3, and subtract the percent we would expect to be in poverty, which is 14.46. When we subtract, we get negative 4.16. Notice that is negative 4.16, so it is below the residual line there. However, if we were to substitute a different point in, let's say the percent of high school graduates is 86%, and we substitute that into the formula that was provided from lesson 8.1, we would obtain that we would expect a value of 11.36 to be in poverty. When I take the actual value of 16.8 and subtract our expected value, we have a positive 5.44 for our red square. Notice that is above our residual line there. The residuals should be nearly normal. This condition may not be satisfied, especially if we have unusual observations that aren't following the trend of all of our data. We can check using a histogram or normal probability plot of those residuals. The third one is the constant variability. The variability of points around the least squares line should be roughly constant. So either looking at the line of best fit itself or the residual line, notice that they're all pretty much falling within the same bandwidth. This implies that the variability of residuals around the zero line should all roughly be constant as well. This is called homoscedasticity. You can check using a histogram or normal probability plot of the residuals as well. Take a look at the plot itself as noting the conditions. Which condition do you feel is not working out? Which condition is the model most obviously violating? The top is the scatter plot and the bottom line is the residual. If you guessed B, awesome. This certainly is not a linear relationship. It looks more curvy in nature, so it could be a cubic regression. It could be a parabolic regression. How about here? Which condition is the linear model obviously violating? The top is the scatter plot and the bottom is the residuals. If you said constant variability, you're correct. Notice at the bottom it's kind of close to the line, but then as we move up into the right, our variability gets wider. So let's say the given information was provided to us from the last lesson is given in this table. How can I find that linear regression formula that was provided in lesson 8.1? How do I get that if I'm given the mean and standard deviation for the percent of those high school graduates and those percent in poverty? So let's say our X value is the high school graduates, our X variable, and those percent in poverty are the Y variable. Notice our correlation is negative, so we should have a negative slope here. Let's first start by finding B sub 1. Let's find B sub 1 so we can identify the slope. This can be found by taking the standard deviation of our Y variable divided by the standard deviation of our X variable and multiplying it by our correlation. In this particular instance, we'll have 3.1 divided by 3.73 times our correlation variable, a value of negative 0.75. So our slope is going to be negative 0.62, which should make sense because our graph is negative. We have our slope that's a negative slope. So if I wanted to interpret this slope, for each additional percentage point in our high school graduation rate, we would expect that the percent living in poverty to be lower on average by 0.62 percent points. Now that we have the slope, let's find our intercept. The intercept is where the regression line intersects with our y-axis, hence why we also call it the y-intercept. The calculation of the intercept uses the fact that a regression line will always pass through that point on the y-intercept. And we know it'll always pass through the point when our x value is 0 and our y value is a number itself. Therefore, we can substitute in our y variable, or our average y value, which is 11.35 from our table, minus our slope, which we already found as a negative 0.62, times our x variable of 86.01. When I use my order of operations to simplify, my y-intercept is 64.68. And I see that that would be about right if I were to continue from my cluster on the bottom right and follow that line all the way to the y-intercept. We would see that it would cross approximately at 64.68. So what does the interpretation of the y-intercept represent in the context of this problem? Take a moment to pause the video and choose either A, B, C, D, or E. Because we would have 0 high school graduates, since our X value represents 0 high school graduates, are expected on average then to have 64.68% of their residents living below the poverty line. Let's talk more on the intercept. Since there are no states in our data set that have no high school graduates, the intercept is of no interest and not very helpful for us. It's also not very reliable since the predicted value of the intercept is so far away from the majority of our data. Here is our final regression line. The expected percent in poverty is equal to 64.68%, or 0.68, minus 0.62% of the high school graduates. The intercept can be found when our x value is 0 and y is expected to equal the intercept. The slope then for each unit in x, y is expected to increase or decrease on average depending upon the slope. It is decreasing if it is negative and it is increasing if it is positive. Also note that just like any other data that we collect, we cannot, the statements are not causal unless the study is a randomized controlled experiment. Let's talk about prediction. We can use the linear model with which we just created to predict the value of a particular response variable for the given value of an explanatory variable. This is what we call a prediction, simply by plugging in a value of x into our model equation. Now we have to be careful because there is some uncertainty associated with the predicted value. We also must be careful to apply a model estimate to values outside the realm of the original data, which is called extrapolation. Sometimes the intercept might be an extrapolation. So be careful. Here is a perfect example. If we were to look at the cluster of data that's given, and we would say that our line of best fit would be that blue line, our linear regression line. Let's say that we would make a prediction for an x value that would place us very close to the top where that star is. However, since we didn't get to see much more data, we would have to be careful because perhaps a cubic function might be a true regression of that function itself utilizing the context of that data. So when in fact the actual value or our predicted value should be much lower than we had anticipated. So be very careful with how you're extrapolating data and what you're using from that regression line, especially if you don't think that it would continually increase, that there are some limitations to it. Other examples of extrapolation might be listed here. Notice that the year is along the bottom, and of course, yes, the year would continue to increase. but a man's age at first marriage probably wouldn't fall below 0 itself. It might increase or decrease or stay the same. So the red dots would be an example of extrapolation, but notice that those red dots aren't actually following the pattern of the data as it continues. It's only that blue line is only using the data for which that it's listed. So it does appear, though, from the early, probably late 1800s through 1950 perhaps, or even into the 60s, using those blue lines, that men's ages certainly do decrease for their first marriage. However, when we grab data from the 50s through 1975, that data not only begins to swing low, but it begins to increase. And further, we probably wouldn't get married before we were born, so that blue line certainly doesn't make sense in the context of the continuation. So perhaps this might be better off utilizing a cubic regression line or even a parabolic one, depending upon more data points that we might find. Let's look at R squared. The strength of the fit of a linear model is most commonly evaluated utilizing R squared, which is taking the correlation value and squaring it. It is calculated as the square of the correlation coefficient. So if I'm given the R squared value, I can find R by taking the square root of R squared. This tells us what percent of variability in the response variable is explained by the model. The remainder of the variability is explained by variables that are not included in the model or by inherent randomness in the data that is collected. For the model we've been working with, our R squared variable could be found by taking our R variable, which is negative 0.62, which was given in our table, squaring it to get 0.38. What do you believe is the interpretation of 0.38 with respect to the data? This tells us that there is 38% of the variability in the percent of residents living in poverty among the 51 states is explained by this model. Let's practice. The following regression output is for predicting annual murders per million from percentage of people living in poverty in a random sample of 20 metropolitan areas. Notice this time I am given the estimate, the standard error, the t-value, and I'm given this probability of greater than the absolute value of t. I can utilize the estimate column to help me write out the linear model. The linear model then is the estimate of murders is given by the formula b sub 0 plus b sub 1 times the poverty percentage. Or utilizing negative 29.901 is our b sub 0 plus our beta sub 1 is 2.559 times the poverty percentage. Let's interpret the intercept. The expected murder rate in metropolitan areas with no poverty is about negative 29.901 per million. This really isn't meaningful at all, considering we can't have negative people per million. But let's interpret what the slope means, that 2.559. For each additional percentage increase in poverty, we expect murders to be higher on average by about 2.559. 2.559 murders per million, to be more specific. Let's interpret what R squared is, and notice in our table we are given R squared. We could also find the correlation coefficient R by itself, and we'll do that in step E. The poverty level explains 70.52% of the variability in murder rates in metropolitan areas. And if I wanted to find the correlation coefficient, I can simply take the square root of 0.7052 to obtain 0.8398. Notice that our R value is very close to 1, so we could say that our correlation has a strong relationship. And your exit ticket. The World Happiness Report is a landmark survey of the state of global happiness that ranks 156 countries by how happy their citizens perceive themselves to be. This year's World Happiness Report focuses on happiness and the community, how happiness has evolved over the past dozen years, with the focus on the technologies, social norms, conflicts, and government policies that have driven those changes. The following scatter plot shows the effect of the measure of the life satisfaction on the measure of freedom from data pulled from the World Happiness Report of 2019. Utilizing the table of values that are given, I want you to describe the relationship between the measure of life satisfaction to the measure of freedom. Calculate the linear regression model. Interpret the intercept in the context of the situation. Interpret the slope in the context of the situation. And knowing that you have r squared there, interpret the r squared variable in the context of the situation as well.